So this video introduces the mean value theorem and how to determine when a function is increasing and decreasing. So you may wonder, if you drop a brick from 12 feet up and it hits the ground in 2 seconds, its average speed then would be, its average velocity would then be 6 feet per second. Well, does it ever go 6 feet per second? Now it should, because if it ever goes less than that speed, it would never actually get to the ground. And certainly if it goes beyond that speed, you would think it goes 6 feet per second sometime. Well, if a pool drains at an average speed of 5 gallons per hour, is there any time when it's draining exactly 5 gallons per hour? Again, it makes sense that it should. We can answer these questions by using the mean value theorem. Now, if f is a continuous function on a closed interval from a to b, and it's a differentiable function on the open interval from a to b, then there has to be a value c in that interval so that the instantaneous rate of change, that's the instantaneous speed, that would be the instantaneous rate of change, or it's also the slope of the tangent line, is the same as the average rate of change, which is the average speed. It's the average change in the volume of the pool in time. It's also the slope of the secant line. It just basically says there's some value of c in between a and b. So if you look at the tangent line is parallel to the secant line that connects the points a, f of a and b, f of b. Now every theorem is broken into two pieces, its conditions and its conclusions. In order to use the mean value theorem, we must first convince ourselves that the function is continuous on a closed interval and it's differentiable on the associated open interval. We can then get the conclusion that c exists. It doesn't tell you how to find c, except that it's an equation that you could solve for c if you wanted to. But oftentimes we don't care. We're just wanting to know that such a c exists. So let's determine if the mean value theorem can be applied to the function f of x equals x squared on the interval from 0 to 4. So if so, we'll then find all the values of c that are guaranteed by that theorem. So we have a little checklist. First one is the function x squared continuous on the closed interval from 0 to 4? And certainly it is. And is the function differentiable on the open interval from 0 to 4? Well, the derivative is just 2x, and that always exists, so then certainly it's differentiable. That means then we can then find all the values of c that satisfy that particular equation. We know what the derivative is, that's just 2x, so we get 2c. And f of 4 minus f of 0 all over 4 is just 4. So you get the equation 2c equals 4. c is 2. And notice that's in the interval. Now if there's more answers, that's okay. We only want one. And if if we get any numbers that are not inside the interval, we would just ignore those. The theorem, though, guarantees there will be an answer to this equation in the interval from 0 to 4. Again, let's determine if the mean value theorem can be applied to the function f of x equals 1 over x squared on the interval from -2 to 2. So first, if you want to know if we can use the mean value theorem, we want to know is the function 1 over x squared is continuous on the interval from -2 to 2. And unfortunately, nope, that's not true. So then we're not guaranteed there is a value so that f prime of c is equal to f of 2 minus f of -2 all over 2 minus -2. And in fact, that would actually equal 0. So it just says we can't be guaranteed that there is a slope somewhere on this interval from -2 to 2, so the slope is 0. And clearly, if you look at it, the slope is always either positive or negative. So then this particular graph never has a slope that's 0. Now, I've implied a number of times that there's a connection between the derivative and whether the function is increasing or decreasing. So let's just remember the definition of what it means to be increasing. A function is called to be increasing on an open interval if for every single two values, a and b in that interval, if a is less than b, then f of a is less than f of b. So we can say this as the input increases, the output increases. Now, you've used this many times in your life. You just don't think of it that way. For example, if I said, look at these two numbers, the square root of 4.5 and the square root of 5.3, which one's bigger? You would probably say the right one. is larger. And the reason is that the input's just bigger. Well, to do that though, you should have in your mind the idea or the graph of the square root function. The square root function is always increasing on the interval from 0 to infinity. The function values just become larger. That is an increasing function. So of course, as x increases, the function value increases also. All right, let's assume then that a and b are any two values in some interval, open or not really, such that a is less than b. And let's assume that the derivative is always positive for all x in that interval. Now, since the derivative exists on the interval and a and b are inside it, then of course, if the derivative exists, then the function is continuous on that interval. That means that f must be continuous on the smaller contained interval inside of I from a to b. Obviously also, if the derivative exists because it's more than 0 for everything in I, a and b are in I, so f is differentiable on the open interval just from a to b. That means I can use the mean value theorem. So there is a c in the interval from a to b, so that f prime of c equals f of b minus f of a all over b minus a. Now I don't care what that c is, but I do notice though that since a is less than b, that means then that the expression b minus a is going to be positive, and I know f prime of c is going to be positive because c is in the interval. The only way that's true then is if this f of b minus f of a, that is also positive. But that means that f of b must be more than f of a. Putting it together then, we have that if a is less than b, then f of a is less than f of b. F is increasing. So we get this nice result that if a function's derivative is always positive on an open interval, then the function is increasing that entire time. So how do we find the intervals then where the derivative is positive and where it's negative? Because that will tell us where then the function is increasing or decreasing. So let's assume though, for simplicity, that the derivative is actually continuous itself on some interval. Then, as a direct consequence of the intermediate value theorem, if the derivative is never 0 in the interval, then the derivative must either be always positive or always negative in that interval. So the only places then that the derivative can change sign is where the derivative is discontinuous, such as where it doesn't exist, or when the derivative is 0. So to find the open intervals on which the function is increasing or decreasing, all we do is just find out all the places where the derivative is 0 or where it doesn't exist in the domain of the function, and also to find out where the function, of course, is discontinuous. These numbers, where the derivative is 0 or where it doesn't exist in the domain of the function, are called the critical values. That's what we had before. That will then take the domain and break the domain up into smaller pieces, over which in every interval the derivative will exist and will be not 0. Therefore, all we do is we pick one value in each interval, we evaluate the derivative at that value, and that will then give us the sign of the derivative for every x value in that one subinterval. We then come back and then use the result I just gave you to tell you where the function was increasing or where it was decreasing. So let's find all the intervals where this function is increasing or decreasing. So to do that, I'll just go and find the derivative first, which would be 4x cubed minus 12x squared, and then I'll solve that the derivative is 0, and I'll solve that for x. That would mean then 4x cubed minus 12x squared would equal 0. That means then that 4x squared times x minus 3 is 0, and that means x is either 0 or 3. You should also find where the derivative does not exist, but the derivative is just a polynomial, so it always exists. I'll just skip that step. Now I'll draw a line. This line represents the domain of the original function f. On that line I put 0, and I put 3. And I put little filled in dots there to remind me that there's actually points that correspond to points on the graph of the original function. Above the line, I'll put the first derivative. Now for every one of these subintervals, just take some value in that subinterval and evaluate the first derivative. We honestly don't care what the answer is. So if you plug 4 in, notice that you would get 4 times 4 cubed minus 12 times 4 squared, and that result is certainly positive. Just add it up. So I'll put a positive here. If you take f prime of 2, now you could do it the way I just mentioned, but notice that the derivative, if you recall, the derivative was that polynomial, but I already factored that as 4x squared times x minus 3. Remember, I don't care what the answer is. I just want to know what the answer would be in terms of positive or negative. If you plug 2 into the factors, this would certainly be positive, while that would be negative. So then the product would then be negative. So this would be minus. If you want, you could then plug in some number less than 0, like f prime of negative 1. But for the same reason, this will also be negative. So this is then negative. So we can then say that f is increasing on the interval from 3 to infinity, because that's where that's where the derivative is positive. And also, I can include 3 also because the function is continuous at 3. So we can kind of glue the result together. You can also say that f is decreasing on the interval from negative infinity to 0, but it's also decreasing from 0 to 3. And because we know the function is continuous at 0, I can glue all that together and say from negative infinity to 3. And I can even close that also, again, by continuity. That is then result. That tells you when the function is increasing and when it's decreasing. Let's try that again. Let's try to find out where this function is increasing and decreasing. To do so, I'm going to need to know what's its derivative. So that will then be f prime of x is equal to 2/3 the power, x squared minus 4 the base. I reduce the power by 1, and then I multiply by the derivative of the inside. Simplifying that, you'll get that's the same as this 2, and that 2 become a 4. There's an x in the product. There's already a quotient because of the division. And then this factor is put back into the denominator as x squared minus 4 to the 1/3 power. There you go. That is the derivative. Now I need to know when is the derivative 0. Let's go ahead and solve that for x. To do that, that would mean that if the derivative is 0, since it's a fraction, the only way that's true is if the numerator is 0. So that gives us instantly that x is 0. That's one of our critical numbers. That's in the domain. Let's also find out where the derivative, where it doesn't exist. Well, now, for a fraction, the only way a fraction would not exist for some kind of choice of x is if the denominator in the end is 0. That would mean then 3 times x squared minus 4 to the 1/3 power, that would be 0. That means then x squared minus 4 would be 0. That means that x would be 2 or negative 2. And those two numbers are actually in the domain of the function. So I count them as critical numbers. Next, I then write a number line. On this number line, I then put the values where the original function is discontinuous. So this has to represent the domain of my function. And on the line, I put in little filled dots for the critical numbers. As the function is continuous here, it just has some kind of change in behavior. So here is your first derivative. Once again, just take for every subinterval, take an x value, and plug it into the derivative. As always, we don't care what the answer is. We care only positive or negative. So if you take some number more than 2, like 3, and plug it into the derivative, clearly the numerator is positive. That would be positive. So the whole evaluation would be positive. So we get a positive here. If you take some number between 0 and 2, like 1, the numerator again would be positive. This would be negative, and it's being taken to a 1/3 power, so that would be a cube root, it would still be negative. So the denominator is actually negative. That would then give you negative. If you look between -2 and 0, like -1, then the numerator would be negative, and the denominator would also be negative. That makes positive. And the last choice, if you pick a negative number like -3, the numerator would then be negative. The denominator would be positive. That division then would be negative in the end. That tells you all the intervals where the function is increasing or decreasing. For example, f increases on 2 intervals. It increases from -2 to 0, and I include the ends because the function is continuous there. And on the interval from 2 to infinity. That's it. That's where the function would increase. Now, from the previous lesson, one of the goals was to try to find the relative max and relative mins in order to discover our absolute max and absolute min. But in the previous lecture, I insisted on using a closed interval. So if we ignore that, then we can really only identify normally quickly our relative max and relative mins. To do so, we use what's called the first derivative test. We simply just use the sign line for the first derivative that I just generated. Because if you assume that f is continuous on some open interval that contains c, and this function is actually also differentiable in that open interval, except possibly at c, there's a couple possibilities that could happen. If the derivative is positive before c, then the function is increasing on that interval. And if the derivative is negative after c, then the function is decreasing on that interval. Well, if it increases and it then decreases, what you must get is something like this. It goes up and then down, but we know the function is continuous in between, so there's a point, and it all glues together. So you must get a relative max. For the same reason, if the derivative is negative before c, that means that the function is decreasing, and if it's positive after c, then the function is increasing. But since the function is continuous at c, there's a point there, and because it's continuous, everything glues together. So then we must have that the function has a relative min there. Now, if those things don't happen, then that means that the function can't have a relative extrema at all there. So that's great. Pretty much the only places we can get relative maxes or relative mins is where the first derivative changes sign and where you have continuity in between. So let's go back to a previous example. If you remember, we had that the sign line for this function was first derivative, and we had -2, 0, and 2. And the first derivative was positive, then negative, then positive and negative. And this function is continuous throughout. So this says the function is decreasing, then increasing, decreasing, and then increasing. But we have points in between, and we know the function is continuous in between, so the graph is all connected. So by thinking this way, you're using the first derivative test. We could then say that f of -2, which is just 0 if you plug it in, that's a relative min. And f of 2, which is also 0, that's also a relative min. And finally, f of 0, that would then be -4 to the 2/3 power. That would then be -4 to the 2/3 power, an awful number. That winds up being negative the cube root of 16. That thing is a relative max. So not only does our work show you where a function is increasing or decreasing, it also shows you where all the relative extrema are, which gets us that much closer to finding our absolute max and absolute min in general. And that's it. That's a quick introduction to the mean value theorem and increasing and decreasing. These results have lots of good uses, which you'll see as we go through the course.